Welcome everyone. In this video lecture, we will solve a rectifier circuit problem which is basically from the Microelectronics circuits book. So the question is, consider the half-wave rectifier circuit with the diode reversed. Okay, so this one is a rectifier circuit, half-wave rectifier, but the diode is reversed here, and let Vs be the sinusoidal signal with 50 volt peak amplitude. So this peak amplitude is simply our plus 15 volt, and another one is our minus 15 volt, you can say, and let R be the 1.5 kilo ohm resistance. So this resistance R value is 1.5 k ohm kilo ohm. Okay, 1.5 kilo ohm resistance is there. So we have to use the constant voltage drop model with VD 0.7. So this one is the diode. Okay, so we have to use constant voltage drop model with VD 0.7. So the same diode is a, this is a non-ideal diode, we can say non-ideal diode. So we have made the same non-ideal diode with a ideal diode. This one is basically a ideal diode. Okay, with a 0.7 volt. This, okay. So I have already made this diagram. So this one is the given thing. So we have to sketch the transfer characteristics. So the transfer characteristics of this half wave rectifier, sketch the waveform of output voltage V naught, average value of V naught we have to find, output voltage, peak current in the diode, how much peak current in the diode, and the peak inverse voltage of the diode we have to find. So first of all, we have to start with the very first thing, that is our A part, that is our transfer characteristics. So I am just writing transfer characteristics, which is just simply our plot between V naught versus Vs. Okay, V naught versus Vs will give the, okay, V naught versus Vs give the transfer characteristics. So now we have to move here. So basically this one is the circuit. Okay, and first of all we have to identify during what time the diode is on or off. So for such situation, we have to first find out the transition voltage. Okay, transition voltage. I am writing it down. Transition voltage. Okay, transition voltage. And during that time, this resistance is R. R is there. The current, say this current I in the circuit will be 0 for the transition voltage calculation, and diode just on, and there will be no current in the just on. Okay, but with no current means the current in the circuit, okay, I equals to 0. So I am just drawing the same diagram here for the transition voltage calculation. I am just removing this one. So diode is just on. Okay, so I am just, this diode is just on. Okay, with, okay, like this. We have assumed that for any voltage Vs, diode is just on. We don't know the exactly the voltage, but during that time this I current across the resistor 1.5 k resistance will be 0. I will be 0. So if we apply KVL, by applying KVL in this loop, okay, KVL in this loop, by applying KVL in this loop will give plus Vs minus plus plus 0.7 and I equals to 0. So this one is R into I. So I is already 0. So it is 0. So we can say Vs equals to 0.7 volt. So basically this Vs equals to 0.7. Okay, right. Vs equals to minus 0.7 volt. Okay, this one. Vs equals to minus 0.7. If you solve this one, simply Vs equals to minus 0.7. Once again I am written. Okay. So that above this we have to identify, means if Vs is greater than equals to minus 0.7, what should be the voltage? Vs less than equals to minus 0.7, diode is on. This one is the deciding factor. Okay, this 0.7 volt minus 0.7 volt will be the deciding factor. Either this side diode will be off, and either this side diode will be on or off. That we have to find. Okay, so for this purpose I just want to use this graph once again. Means this one is the Vs. So just after finding transition voltage, that Vs equals to minus 0.7 equals to transition voltage. This Vs equals to 0.7 volt minus 0.7 volt. I am saying this one is a transition voltage. Okay, why it is very useful, I will show you. So now this Vs equals to 0.7, I'm just drawing a line. Okay, Vs equals to 0.7, this one is basically a t axis. Vs equals to 0.7, a line parallel to the x axis, there is minus 0.7 volt. Okay, so this whole line is Vs equals to 0.7. So we have to decide above this line Vs equals to this, diode will be on or off. Above, below this line diode will be on or off. So for example, if I am saying Vs, that is our greater than equals to minus 0.7, means above this Vs, above this greater than 0.7 in the up case. So if this one is minus 6, Vs may be either our minus 0.6, 0, and even plus 1 volt. Okay, anything 2 volt, 2 volt up to 15. Okay, if this one is saying I am 15, so this one is plus 15, but there is a negative side, cathode side, so diode will be in the reverse bias. So diode will be reverse bias. So for this one diode will be reverse bias, that we have to think. And it is very simple, reverse bias or diode will become off. So above this one diode will become in the off state. Okay, and so Vs greater than equals to 0.7, the diode become off. Okay, by taking any example you can say Vs 1 volt, anything plus 1, then this one is minus 0.1. So this value will be much positive, then this one is cathode, so this is reverse bias. So diode off, or simply I am writing reverse bias as a RB. Okay, so this one is one case. So when the diode is reverse bias, in this case diode will be in the reverse bias, this will be open circuited. So if we make the circuit for this one, okay, I am just making here basically for this one. Okay, diode will be reverse bias. Okay, so there will be zero current in the circuit. So V naught will be simply 0 volt when diode will be the reverse bias for Vs greater than 0. It is very useful thing. Okay, useful information we can say. So V naught equals to 0 volt. So this one is the circuit, corresponding circuit. When we are taking all these value, this one will be the 0. Okay, so now next what we can do for Vs less than minus 0.7 volt, what we can do for this purpose, again think Vs less than 0.7. So less than means it may be our Vs value. Vs value may be our less than 0.7, like minus 0.8. Okay, or minus 1, minus 2, dot dot up to minus 15 we can go. Okay, so when this is negative, okay, so when this is negative, okay, so this diode will become forward bias. So diode become forward bias, and diode become on and forward bias. Very simple thing. Okay, so when diode is on, Okay, for that one I am just making the circuit here. Diode is on. Okay, so what we can do, this will, okay, and this will be 0.7 volt minus plus. So the output voltage V naught we can write as plus Vs plus 0.7 minus V naught equals to 0. So V naught equals to Vs plus 0.7 volt. Okay, so this one will be the output voltage when the diode is on. Okay, so diode is on, so the output value will be 0.7. Okay, so this part is clear. So once again I am writing one line. Then Vs is less than equals to minus 0.7, diode become on. When it is Vs is less than minus 0.7, diode on, and Vs greater than minus 0.7, diode off. So that thing will be clear to you. Then V naught equals to 0, and in this case then when the diode is off, sorry, V naught equals to 0, and when diode is off, this V naught will be 0, and when diode is on, okay, for this one this would be Vs plus 0.7. Okay, so now we have to plot this one. V naught Vs curve is we have to plot. So what we can do, V naught Vs. Okay, so V naught equals to Vs, we can say this one is a y equals to x line. Then Vs plus 0.7, Vs plus 0.7, so this curve will go up by 0.7. Okay, so I am just making like this. So this point is nothing but simply V naught equals to Vs plus 0.7. Okay, so this point will be our simply our minus 0.7, sorry, 0.7 we can write, and should be 0, and this point will be 0, and the other point means this one. When this Vs is 0, so 0.7, so 0, 0.7. Okay, and diode will conduct, diode on for Vs less than 0. So during that time this line will be there. So this will be the line that is we are interested. Okay, and above this will be 0. So the this one will be the V naught equal to Vs plus, and this one will be the 0. So the overall characteristics we can say for the V naught and Vs is somehow looks like this. Okay, the same thing is there. Okay, this one is minus 0.7. So this one is the first part. Okay, very simple, but you have to plot, and we have to just go through this observation, okay, for this curve, and you have to draw V naught versus Vf. So this one is the first part for the calculation, for the sketch of transfer characteristic. Now we have to go for the output waveform. So output waveform is easy to draw. Okay, so second part, output waveform. Okay, for output waveform, what we have to do, that we have to discuss. For the output waveform, what we are doing, okay, I am just again Vs as a T. Input voltage we know. Okay, for first positive. Okay, Now transition line we have already find out. Say this one is the transition line. Somehow Vs equals to minus 0.7. Above this the diode become off, and below this the diode become on, that we know, okay, in the earlier case. Okay, so above this, below this line diode will be on, so V naught equals to same expression, and V naught equals to 0 for above this. So for example, now I am just saying this point is theta, and this point I am saying pi minus theta. We are just considering this one, this whole, okay, having total radian pi radian. So this is this angle is theta, then we can find this one pi minus, this will be pi minus theta. So the output waveform will be a start from this point, output waveform will be a start from this point and go like this, it will go like this, and okay, and it will again start and go like this, and it is go like this. Mm, okay, this value will be V naught equals to Vs plus 0.7. Okay, for the below portion will be same as that of. So this one is the output response. Very clear from this curve we can easily say, and this angle will be theta because this one is Vs plus 0.7. Vs is there plus 0.7. So if this one is V naught, sorry, Vs, so it should be Vs plus 0.7. So here negative 1 is there, so plus, so it should be cos ring. Okay, so this theta can be easily calculated by using, if this one is 15 sine theta and 0.7. So sine theta will be 0.7 by 15. So this will give the value of theta equals to 2.67 degree. Okay, so this is the output waveform. Output waveform can be easily draw by using this one first, but all the time you just try to write the draw the this line. Then okay, before that it is on. So when it is on, from this point to this point, it will be go like this. Okay, so like that we can draw this one output waveform, and it will start from this end and it will ends at the pi minus theta. So conduction angle we can say the conduction angle will be for that particular half should be pi minus theta. This one minus this one, so pi minus 2 theta will be the conduction angle. So this is the output waveform. Okay, this is simple output waveform. From the very first figure also we have already draw this one. So if we make this one, zero point 0.7 is there. Okay, so okay, this is one line. Okay, so up for this point it will go like this. Okay, and above this it will 0. Okay, for the first half, so output waveform will be like this. So very simple, and this will be Vs equals to, oh sorry, V naught equals to Vs plus 0.7, that we have already done. Okay, so now we have to very fundamental output waveform response is, okay, output response first, second part. Now the average value of V naught. So average, what is the average value of V naught? So here what we can do, average value of V naught. So in this average value of V naught there must be some calculation, but we have to know the calculation, how to do the average value of calculation. So for average value of calculation, what we have to do, I am taking this one for what should be the average value. So for the average value what we will do, I average equals to 1 by 2 pi, okay, negative, because this is negative direction, and output response from means the area theta to pi minus theta we can say. Okay, and the sinusoidal signal will be, I am saying 15 sine phi minus 15 sine phi minus 0.7, because in the same signal if we have reduced minus 0.7, it will go give the same response into this. Okay. Okay, so now this one is a simple average calculation. So here what we can do, minus 1 by 2 pi theta, so make it theta. Okay, so what we can do, first we will do for this one 15 sin phi. So what we can write, minus 15 cos phi, sin phi integral is cos phi. Like this we can write. Clear? We can write it pi minus theta to theta minus 0.7 in bracket again. This should be phi. So we can write as simple phi for d phi, and this should be pi minus theta to theta. Simple calculation is there. I am just trying to do the calculation. So 1 by 2 pi minus 15. Okay. Then what we can write, cos pi minus theta minus cos theta. Okay, for this one minus 0.7, the pi minus theta. Okay, so one more line I am writing. I am doing it step by step, means how to do calculation, because it is also important to do the calculation how to, this all are the average value. So minus 1 by 2 pi cos pi minus cos theta. So one can write minus 15 into minus cos theta minus cos theta. Okay, once again one more line, minus 0.7 pi minus 2 theta. Is it okay? This one there is no mistake, huh? Okay, minus 15 minus cos theta, then minus 1 by 2 pi. Okay, then we can write plus 15 into minus 2, so minus 15 into minus 2 cos theta, we can write it 30 cos 2 theta. Okay, or do like this, 15 into 2 cos theta. Okay, minus minus plus 52 cos theta minus 0.7 pi minus 2 theta. Once again one more line. Okay, okay, now we will go fast. Okay, now this one is basically we have to think about in radian, because theta is in our degree. Theta is in degree 2 point, so 180 degree equals to pi radian. Okay, so better to convert it into radian. So what we can do, to cos theta, theta is 2.67. So 2.67 pi by 180, because 2.67 degree. Okay, so 180 degree equals to pi radian. So 1 degree equals to pi by 180. So 2.67 will be pi by 180 into 2.67. Okay, so that's why I am writing 2.67 pi by 180 as a radian, minus 0.7 pi minus 2 into again theta can be written as 2.67 pi by 180 minus 1 by 2 pi. Okay, and if we solve in calculation, this in calculator, it will give around 29.9999908. I have already calculated, that's why I am writing minus 0.7 here one. Okay, 180 pi minus, if we solve this one, 5.34 pi by 180. Okay, okay. Okay, next what we can write, minus 2 pi, and then okay, now I will solve 999,008 minus, if you solve the entire term, it will come minus 2.13387,445. I have already calculated, that's why I am writing directly. Then if we solve this one, it will come minus 27.86611,563 divided by pi 2 pi. Okay, and if we finally solve, it will come minus 4.43 volts. So average value will be minus 4.43. Okay, it can be done using this concept minus 1 by 2 for the negative one, theta to pi minus theta, 15 sine phi, because theta is the lower limit, pi minus theta, so I am taken phi. So we are integrating with this, and after solving in all in radian, what we observe that the average value will be like this. Okay, so now next is our what is next? Peak current in the diode. Peak current. Okay, peak current in the diode. D part. I'm writing peak current in the diode we have to find. So we assume that the voltage, maximum voltage we are giving 15 volt, and diode will be like this, means okay, or better to means diode will be forward bias. At what condition? When we are giving the maximum voltage, that is our, make it minus plus. Okay, I am writing this as a minus 15 volt, and this one will be 0.7 volt. So that will be on, and this one will be the current. Okay, R is there. Okay, so if this current is the maximum current, because during that time forward bias, that will be forward bias for this minus 15 volt, because this one is the diode. So diode will be maximum current will give only when this one is minus 15 volt. So what we can do, we have to just apply KVL. So minus 15, okay, minus 15 minus 0.7, sorry, minus 15 minus plus minus plus, okay, plus 0.7 minus I into R will be our how much, 1.5 K, 10 power 3 equals to 0. So what we can write, I into 1.5 into 10 power 3 equals to 15 minus 0.7, 14.3. So the I current, the maximum I current will be 14.3 by 1.5, 10 to power 3. Okay, so 14.3 by 1.5 milliampere, and if we solve, it will come 9.53 milliampere. Okay, now finally E, the peak inverse voltage. So peak inverse voltage is the maximum reverse voltage across the diode. So for that one, what we can say, first we have to give the positive voltage to make the diode reverse bias. Okay, so there will be no battery model, so make it like plus minus, it should be PIV, and this should be VS. So VS minus PIV will be 0. For the half wave rectifier, the peak inverse voltage will be also the VS value, so maximum value will be 15 volts. So this is all about this question. It is a very good question, and it is from the microelectronic circuit. So we have to very careful about the calculation, means how we are calculating 180 degree equals to pi radian, means by using the this average calculation you can find the average value, how we are plotting the output waveform, and a sketch of the transfer characteristics we have done in this problem. So thank you for watching this video.